Welcome to this video. Today, we'll be diving into LeetCode problem number 1897, titled Redistribute Characters to Make All Strings Equal. This is an interesting problem that involves analyzing the frequency of characters across multiple strings. In this session, we'll break down the problem step by step, explore the key concepts, and walk through an efficient solution. Let's get started. In this problem, we are working with an array of strings called words. Each string in the array is composed of lowercase English letters. The goal is to determine if it's possible to redistribute the characters from all the strings such that every string becomes identical. For example, if you have 3 strings, you would need to rearrange all the characters so that each of the 3 resulting strings is exactly the same. The input to the problem includes an array of strings, where the array can contain between 1 and 100 strings, and each string can be up to 10,000 characters long. The output is a Boolean value, true if redistribution is possible, and false if it is not. Let's look at some examples to better understand the problem. Consider the first example, where words is an array containing the strings ABC, ABC, and BC. The output for this example is true. Here's why: we can combine all the strings into one single string by concatenating them, resulting in ABC. Now, we can evenly divide this combined string into 3 identical strings, each of which is ABC. Since we were able to successfully redistribute the characters so that all 3 strings are equal, the output is true. In contrast, let's look at a second example with words equal to AB and A. In this case, the combined string is ABA, but it's not possible to divide it evenly into 2 identical strings because one string would end up missing the character B. Therefore, the output here is false. Now, take the third example where words is AAA, AAA, and AA. When we combine all the strings, the result is AAAAAAAA. However, this combined string contains a total of 9 characters, and since there are 3 strings in the original array, we need to divide the characters evenly into 3 parts. Since 9 is not divisible by 3, it's impossible to create 3 identical strings. Therefore, the output is false. These examples illustrate that the redistribution of characters depends on both the total number of characters and their distribution across the strings. To summarize, we need to ensure that the total number of each character in the combined string is divisible by the number of strings in the array for redistribution to be possible. Some constraints and key insights help clarify the problem further. The length of the words array can range from 1 to 100, and each string can contain between 1 and 10,000 characters. Importantly, the total number of characters across all strings will not exceed 10,000. Additionally, each string consists only of lowercase English letters. A key insight for solving this problem is that the total count of each character across all the strings combined must be divisible by the number of strings in the array. This ensures that every string can receive an equal share of each character. There are a few edge cases to note as well. If the array contains only a single string, redistribution is always possible because there's no splitting required. On the other hand, if certain characters appear with unbalanced frequencies that cannot be evenly distributed, the output will be false. Finally, the solution should also handle cases with large input sizes, where the constraints are pushed to their limits. To solve this problem, the approach involves counting the frequency of each character across all strings in the array. Once we have the frequency of each character, we check if each frequency is divisible by n, where n is the number of strings in the array. If all frequencies are divisible by n, that means we can evenly distribute the characters, and the function should return true. Otherwise, if even one character's frequency is not divisible, redistribution is not possible, and the function should return false. This method ensures that we efficiently determine whether redistribution is possible while adhering to the constraints of the problem. To solve the problem of redistributing characters to make all strings equal, we start by exploring different approaches. The first is the brute force approach. Here, the intuition is to examine every possible way to redistribute the characters among the strings. For each string, we calculate the frequency of each character and then attempt to rearrange these frequencies uniformly across all strings. This requires nested loops, one to count the frequencies and another to test redistributions. The main drawback of this approach is its inefficiency, as the time complexity is O, n asterisk m, where n represents the number of strings and m is the average length of the strings. This makes brute force impractical for larger inputs, as it becomes computationally expensive and slow. Instead of brute force, we can use an optimized frequency check, which is the chosen approach for this problem. The idea here is to focus on the total frequency of each character across all strings. If the total count for every character is divisible by the number of strings, then redistribution is possible. The key insight is that making all strings identical depends solely on this divisibility condition. To implement this, we first count the frequency of each character across all strings using a single frequency array. Then, we verify if each character's total frequency is divisible by the number of strings. This approach is efficient, as it requires just one pass to count frequencies and another pass to check divisibility, resulting in a time complexity of O(n*m). Additionally, while another alternative approach involves sorting and comparing frequency distributions, sorting adds unnecessary computational overhead, making it less suitable for larger inputs. The optimized frequency check is the chosen strategy because it is both simple and efficient. The core insight is that redistribution relies entirely on the divisibility of character counts by the number of strings, which allows for a direct and elegant solution. When comparing the approaches, brute force is clearly inefficient due to its reliance on nested loops, making it impractical for large inputs. The sorting approach, while valid, introduces additional overhead without providing any advantage over the optimized method. On the other hand, the optimized frequency check balances clarity and efficiency, solving the problem in linear time relative to the input size. This strategy not only minimizes unnecessary computation but also directly addresses the problem requirements, making it the best choice for effectively solving this challenge. In this problem, we are tasked with determining whether the characters from multiple strings in an array can be redistributed in a way that makes all strings identical. To solve this, we need to focus on the total counts of each character across all strings. If these counts can be evenly divided by the number of strings, then redistribution is possible. The first step is to count the frequency of each character across all strings using a dictionary. This cumulative frequency will tell us how many of each character we have in total. Next, we check if these frequencies are divisible by the number of strings. If any characters count fails this test, it means an even redistribution is impossible, and we return false. Otherwise, if all characters pass, we return true, indicating that redistribution is achievable. This approach ensures that we only redistribute characters when it's mathematically possible to make all strings identical. To better understand this, let's look at an example where the input array is ABC, AABC, BC. The first step is to count the cumulative frequencies of each character. Starting with ABC, we get A1, B1, C1. Adding the characters from AABC, we update the counts to 3, B2, C2. Finally, with BC, the counts become 3, B3, C3. Now, we move to the divisibility check. The total number of strings is 3, so we check if each character's total count is divisible by 3. For A, the count is 3, which is divisible by 3. The same holds true for B and C. Since all characters meet the condition, we can conclude that redistribution is possible. The result for this example would be true. With all characters passing the divisibility check, the function returns true, confirming that redistribution is possible. This leads us to some key insights. First, checking divisibility ensures that each character can be evenly distributed among all strings. If any character fails this check, redistribution becomes impossible, which is why an early exit in such cases is an optimization that saves computation time. Additionally, the use of a dictionary for frequency counting is efficient, as it allows quick updates and lookups. In terms of complexity, counting frequencies requires processing all characters in the input, which takes O(m) time, where m is the total number of characters. Checking divisibility involves iterating through the dictionary, which is O(k), where k is the number of unique characters. Thus, the overall time complexity is O(m plus k). The algorithm is also space efficient. The frequency dictionary only needs to store counts for up to 26 lowercase English letters, making its space complexity O(1). This ensures the algorithm can handle large inputs effectively. Now, let's discuss some edge cases. If the input contains empty strings, the algorithm handles them naturally, as no characters need redistribution. For an input with just one string, redistribution is trivial since the single string is already identical to itself, so the result is true. Additionally, the algorithm is designed to handle large inputs efficiently without compromising correctness, as it only processes the total characters and unique frequencies. Here's the complete implementation of the algorithm in Python. First, we use the counter class to count frequencies across all strings. Then, for each character, we verify if its count is divisible by the number of strings. If not, we return false immediately. If all characters pass the divisibility check, we return true. Let's walk through an example to solidify your understanding. For the input, ABC, AABC, BC, the cumulative counts are A, 3, B, 3, C, 3, all counts are divisible by 3, so the output is true. In another example, UB, the cumulative counts are A, 2, B, 1, here, the count for B is not divisible by the number of strings, which is 2. Thus, the output is false. These examples demonstrate that the algorithm correctly handles both success and failure cases, ensuring its robustness across different inputs. The provided code solves the LeetCode problem number 1897, redistribute characters to make all strings equal, using a straightforward and efficient approach. The goal is to determine if the characters from all strings in the array can be redistributed so that all strings become identical. First, the solution imports the counter class from Python's collections module to facilitate counting character frequencies. The main function makeEqual takes a list of strings words as input. 1. Determine the total number of words. The length of the words list is stored in number_words. This value is essential for verifying whether the total counts of each character are evenly divisible by this number. 2. Count character frequencies. A counter object total_char_count is used to aggregate the frequencies of all characters across the input strings. Each word is processed, and its characters are added to the cumulative count using the update method. 3. Check divisibility by number of words. The function iterates through the items in total_char_count, which provides each character and its total occurrences. If any character's frequency is not divisible by number_words, the function immediately returns false, indicating that redistribution is not possible. 4. Return true if valid. If all character frequencies pass the divisibility check, the function returns true, confirming that redistribution is feasible. This implementation ensures efficiency by processing all characters in O(n) time, where n is the total number of characters across all strings. The use of counter makes the frequency calculation concise and clear. Edge cases, such as an empty list or strings with no overlapping characters, are naturally handled by this approach. The solution is both compact and highly readable, making it an ideal choice for this problem. This is the Java implementation of LeetCode problem number 1897, redistribute characters to make all strings equal. The logic mirrors the Python implementation, using Java-specific features such as the hash map for counting character frequencies. Key differences include explicit type declarations, the use of the map interface for character counts, and the char array for iterating over string characters. The solution iterates through the words array, counts character frequencies, and checks divisibility by the number of words. This ensures that characters can be evenly redistributed among the words. The problem asks us to determine whether we can redistribute the characters from an array of strings in such a way that every string in the array ends up containing the exact same characters with identical frequencies. If this is possible, we return true, otherwise, we return false. For example, consider the input words equals ABC, ABC, CC. Here, we first calculate the number of words, which is 3. This will help us determine the feasibility of redistributing the characters. Next, we need to carefully analyze the character frequencies across all the strings in the array and verify if the redistribution can be done evenly. To solve the problem, we begin by calculating the total character frequencies across all strings in the array using the counter class from the collections module. First, we initialize total_char_count as an empty counter. Then, for each word, we count its character frequencies individually. For the word ABC, the frequencies are A1, B1, C1. For AB, we get A2, B2, C2. Finally, for CC, the frequencies are C2. Adding these together gives us a combined total _char_ count of A, 3, B, 3, C, 5. Now, we check if each character count is divisible by the number of words, which is 3. The counts for A and B are both divisible by 3, but the count for C is 5, which is not divisible by 3. Therefore, it's not possible to redistribute the characters evenly across all strings, and the output is false. In another example, we examine the input words equals AA, BB. First, we calculate the number of words, which is 2. This forms the basis for checking the divisibility of the character counts. Next, we count the character frequencies. For the word AA, the frequency is A2. For BB, it's B2. Combining these gives us a total character count of A2, B2. This indicates that we have 2 occurrences of A and 2 occurrences of B across all strings combined. Now, we check if each character count is divisible by the total number of words, which is 2. For A, the count is 2, and since 2 divided by 2 equals 1 with no remainder, this is valid. Similarly, for B, the count is 2, which is also divisible by 2. Since all character counts are divisible by the total number of words, it is possible to redistribute the characters evenly, and the output is true. In the next scenario, we'll examine how this logic applies to a single word case. When there is only one word in the input, such as words equals ABC, the solution simplifies significantly. First, we calculate the number of words, which is 1. Next, we count the character frequencies for the single word. For ABC, the frequencies are A1, B1, C1. Since there's only one word, the total _char_ count remains A1, B1, C1. Now, we check if each character count is divisible by the total number of words, which is 1. For A, B, and C, each count is 1, and 1 divided by 1 equals 1 with no remainder. This means all characters can be redistributed evenly, and the output is true. When analyzing the time complexity of our solution, we can break it down into 3 main steps. First, finding the total number of words in the input list is straightforward and takes constant time, 1, as it only involves checking the length of the list. Next, we compute the frequency of each character across all the words. This step involves iterating through each word and updating the counter object based on the characters in the word. If we let n represent the total number of characters across all the words, the time complexity for this step is n, since we process each character exactly once. Finally, we check if the frequency of each character is divisible by the number of words. Here, we iterate over the distinct characters stored in the counter, performing a modulus operation for each. If C is the number of unique characters, this step takes C time, as each operation is constant time. These 3 steps together form the basis of our time complexity analysis. Now, combining these steps gives us O1 for the first step, ON for counting character frequencies, and OC for checking divisibility. Since the number of unique characters, C, is typically much smaller than the total number of characters, N, the dominant term is ON. Therefore, the overall time complexity of the solution is ON. Turning to space complexity, the main contributor is the counter object, which stores the frequency of each unique character. If there are C distinct characters, the counter will use OC space. Additionally, temporary variables such as number_words, word, and char consume constant space, O1. Thus, the space complexity primarily depends on the number of distinct characters, C. In conclusion, the overall space complexity is OC. In the worst case, where all characters are unique, C could be proportional to n, making the worst case space complexity ON. Comparing this optimized approach to a brute force method, we see significant improvements. A brute force approach might attempt to manually redistribute characters, potentially iterating over all combinations or simulating redistribution for each character. This could result in a time complexity of O(n*(c), or worse, which is far less efficient. Our optimized solution avoids this inefficiency by leveraging the counter object to aggregate character frequencies efficiently and performing divisibility checks in a single pass over the frequency map. This use of modular arithmetic ensures that these checks are constant time operations, further improving the overall efficiency. Finally, let's consider the best, average, and worst-case scenarios for our solution. In the best case, where the input contains minimal distinct characters, such as when all words consist of the same repeated character, the time complexity remains O, N, and the space complexity is O, C, with C being very small. In the average case, where characters are reasonably distributed across the words, the complexities remain O, N, time and O, C, space, which is typical for most inputs. The worst case occurs when every character in the input is unique, such as when each word is a sequence of distinct characters. Here, the space complexity reaches O, N, as C becomes proportional to N, but the time complexity still remains O, N, as each character is processed only once. Mathematically, the time complexity is dominated by the step that updates the counter for all characters, which processes each character exactly once, resulting in O, N. Similarly, the space complexity comes from the counter, which holds one entry per unique character, simplifying to O, N in the worst case. This analysis confirms the efficiency of the solution in all scenarios. One of the most common mistakes when solving this problem is failing to account for the total count of each character across all strings. It's not enough to check individual strings, you need to ensure that the total count of each character is divisible by the number of strings to redistribute them evenly. Another pitfall is neglecting edge cases, like when there's only one string in the input. In such cases, the answer is always true since there's nothing to compare or redistribute. Similarly, mishandling empty strings can lead to runtime errors, so it's crucial to handle these cases explicitly in your code. Additionally, some approaches lean on inefficient solutions like sorting the strings or using nested loops to compare characters. These can unnecessarily increase the time complexity, whereas counting character frequencies with a dictionary or an array is far more efficient. Lastly, in variations of this problem that include non-alphabetical characters, many solutions fail because they assume only lowercase letters. It's important to generalize your solution to handle any possible character set as specified in the problem constraints. Overcomplicating the validation logic is another common issue. Instead of sticking to the straightforward approach of counting frequencies and checking divisibility, some solutions attempt to manually redistribute the characters. This not only makes the solution harder to debug but also introduces more opportunities for errors. The key insight here is to focus on the total frequency of characters. If the total count of each character is divisible by the number of strings, redistribution is possible. This is a recurring pattern in problems involving counting and redistribution, and the modulus operator often plays a central role. It's also helpful to discuss edge cases during interviews, such as handling a single string, empty strings, or strings with no overlapping characters. As for optimization, stick to a single pass to compute character frequencies across all strings. This avoids the overhead of nested loops or additional data structures, keeping your solution clean and efficient. This problem is closely related to other LeetCode problems that involve character counting or manipulation. For example, in LeetCode 242, valid anagram, you use similar logic to compare character frequencies. In LeetCode 383, ransom note, the focus is on verifying whether the characters from one string can be redistributed to form another. LeetCode 49, group anagrams, takes this further by grouping strings based on their character counts. Finally, LeetCode 791, custom sort string, involves manipulating character frequencies in a specific order. As for solving this problem, two main approaches are worth discussing. The first is using a hash map or an array to count character frequencies across all strings, which works efficiently in O, N, time if the character set is predefined, such as lowercase letters. The trade-off here is that it assumes a fixed character set. The second approach is sorting based, where you sort the strings or their characters and then compare them. While simpler to implement, this method is less efficient, with a time complexity of O, N *k log, k, where k is the average string length. Another approach is to simulate the redistribution process manually, attempting to move characters from one string to another. However, this method is highly inefficient and prone to errors. It introduces unnecessary complexity and is generally not recommended, especially in an interview setting. While it might seem intuitive to try and visualize the redistribution, it's far better to focus on the mathematical properties of the problem, like character frequency and divisibility. Sticking to efficient, frequency-based approaches will not only save time but also help you avoid the pitfalls of overcomplication. Great job following along. To recap, we solved problem number 1897 by analyzing character frequencies and ensuring divisibility by the number of strings. This approach demonstrates the importance of string manipulation techniques and efficient algorithm design. Thank you for watching, and don't forget to like, subscribe, and stay tuned for more coding content. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!